All right, hello AP Chemistry students here at Fruitport High School. So we are ready to do our next distant learning lesson. And today's goal, I want you to be able to know a couple trends on the periodic table that are based on the atom. So recently we've been talking about electron configurations and the quantum mechanical, the model. We're going to combine that with some trends. So you'll see I'm wearing my blue and white. I'm recording this on Wednesday, blue and white day, kind of a weird day to be doing blue and white spirit week when you're not in class, but here we go. So if you, let me I kind of put this up there. So the periodic table trends, what we have here is that, well, let me just kind of give you some notes. You need to know what and you need to know why. The what will be like, well, which atom is bigger, or which ion is bigger, or which element has a higher electronegativity. So we're going to have to learn what those vocab words mean and the pattern on the periodic table. And just knowing the pattern is very valuable. We'll use it all the time. But the more advanced part is going to be the whys. And when you go to say why, we can't use the periodic table location to tell us why, all right? So we can't say, well, potassium's bigger than sodium because it's lower on the periodic table. That's how we might know which is bigger and which is smaller, but the physical workings of the atom have to be described differently, okay? So we want to make sure that we talk about the protons and the electrons and the energy levels. Those are the three key components to understand why atoms have the trends that we have, okay? And so we'll want to be specific with the details so you can don't just say they have more electrons, like give me the exact numbers. How many do we have? And this is practical. It says AP test high priority, okay? So the first trend to know is this, atomic size. So atoms get bigger as they go down the periodic table. This is what this chart's supposed to do. And atoms also get bigger as we go across the periodic table to the left. Okay? Now, I'm going to grab a periodic table. Okay, well, sorry that I didn't want to start recording over, so you have to deal with that. So here I have a periodic table that we can look at in the screen in the corner. And if you don't want to memorize this fact that atoms get bigger as you go down the periodic table, and you don't want to memorize this one, you can memorize one trend. They get bigger as we go towards francium. So if you can see in this little screen here, can I make this bigger for a second? Yeah, I can. If I asked you, what's bigger, and we asked you, what's bigger, a carbon atom or a germanium atom? You would pick germanium. It's lower on the periodic table. Or what's bigger, an aluminum atom or a chlorine atom? And you would pick aluminum because it's closer to the francium corner. It's farther to the left. That's a little counterintuitive because chlorine's got more protons and more neutrons and more electrons, but it's actually smaller in size when we compare it to aluminum. And if we have diagonal, like what's bigger, oxygen or phosphorus? Phosphorus is both lower, so it's bigger, and farther to the left. But this slide has a limitation. If we ever ask elements that are diagonal in this direction, what's bigger or smaller, we don't know. We don't know always. Like if I ask you, what's bigger, carbon or sulfur? Well, we have contradicting facts. Sulfur's lower on the periodic table, but carbon's farther to the left. So which one do we use? And the answer is that we don't know. We might not know. We might have to look it up in a book instead of using a periodic table trend. Okay? So those are the easy questions on a test. What's bigger? The harder question is going to be explaining why. And atomic size, this why we get bigger going down is bigger, is different than this why. So let's talk about that. If we are asked a question to explain why atoms increase in size as we move down the periodic table, or which of these is bigger and explain why, and the atoms are located up and down on the periodic table, here's what you need to do. You have to say that, oh, well, atoms lower on the periodic table have more electrons. And those electrons are filling more energy levels. And if you remember from the lesson earlier this week, energy levels mean size. It physically means bigger or farther from the nucleus, a bigger size. Okay? So there's also this concept called shielding. Shielding is where inner electrons block the outer electrons from being attracted to the size. So let me do some pictures here to kind of just reinforce this, see if this helps. Okay, so if we were to draw a lithium atom, okay, if we were to draw a lithium atom, lithium has 3 electrons. And if we were going to do the Bohr model, we'd put 3 protons in the nucleus, and the first ring would get 2 electrons, and that's full, and then the second ring gets an electron. But if we look at sodium, right underneath lithium on the periodic table, that has 11 electrons. So we have 11 protons, and 2 electrons go in the first ring, and you'll remember 8 electrons go in the second ring. I like to put them in pairs at this point because we kind of did those up and down arrows electron configurations. And then sodium needs a third ring to start filling in its 11th electron, right? 3 energy levels versus 2 energy levels, right? This will be a larger size, okay? So as you go down the periodic table, we have this effect. The shielding comes from this little phenomenon. The positive charge is the nucleus right here, and it's attracted, right? These electrons are attracted to the positive nucleus. Well, this electron kind of gets blocked a little bit from the electrons that are spinning in the first and second energy level, so it's not quite as attracted. Analogy I like to use is a magnet. If a magnet's holding up one piece of paper, the attraction between the magnet and the other side of the metal is blocked by a piece of paper. That is probably okay, but if you try to use a magnet to hold up 10 pieces of paper on your refrigerator, the 10 pieces of paper might block the attractive powers. So if you have like a really big atom with like 7 or 6 energy levels, those outer electrons are really far away from the nucleus, okay? Which charges them up. Okay, now to go back to size, we have a completely different answer if we talk about this trend. Why do atoms decrease in size as we move to the right of the periodic table? We get smaller as we go this way, and we get bigger as we go this way. Why do we get smaller as we go this way? And so this one's kind of hard to understand. So you might be like, well, aren't we adding more electrons just like we did in the previous question? And the answer is yes, but we're not adding electrons to new energy levels. They're in the same energy level, which might look like the same size. Let me give you an example. So I'm going to use my sodium picture here. Let me make this a little bit bigger. So I have my sodium. And then if we were to compare it to another element in the same period, so here's magnesium. Let's use a phosphorus. Phosphorus has 15 electrons. And so then we'd have 15 protons and some neutrons in the nucleus. We're not concerned about the neutrons. But the first energy level in the Bohr model holds 2 rings. Right? The second energy level holds 8 rings. The second energy level holds 8 electrons. And then the third energy level, which is the same size, maybe my circle's not exactly perfect, it's the same size as this one, but this one will have 5 electrons. 1, 2, 3, 4, 5. And notice that we haven't had to add a new ring, okay? So you might be thinking that the sodium and phosphorus should be the same size because their electron cloud is the same. But if we were to take a closer look here, there's a second variable changing. As we're adding electrons, we're adding more protons to the nucleus, which makes this nucleus with 15 protons stronger positive pull, if you will. And this will take all of the electrons and all of the levels, and they will shrink a little bit closer. All of this whole ring gets pulled in a little bit smaller every time you add a proton. And so 11 protons trying to attract 3 energy levels close by is not as powerful as 15 protons that will draw electrons closer. Okay? Pretty hard to understand, but we have 2 different slides, 2 different sets of notes here that for explaining why. So if I was going to ask why is sodium and phosphorus, which one's bigger and why, I have to use this slide to give the explanation. But if I asked what's bigger between lithium and sodium, because they're up and down on the periodic table, I would use the previous slide as a way to understand that. All right, this is pretty confusing, pretty challenging, and we will spend some more time on this in class, okay? But I want to give you a start now. All right, we're going to keep going. Our next pattern to look at is first ionization energy. So the first thing that you'll probably want to do is understand what is the definition of ionization energy. So the first ionization energy is the energy required to remove 1 electron. So if an atom loses an electron, energy has to be used because the electron negative is attracted to the positive proton. So to pull it apart requires a little bit of thrust of energy. And yeah, so there's a pattern on the periodic table for first ionization energy. By the way, second ionization energy would be what if you wanted to remove a second electron after you've already removed one. And remember, when an atom loses an electron, it has a charge, and it's called an ion now. And so there's a pattern that at the top of the periodic table, the electrons and ionization energy is very high. And also to the far right, we increase. So the francium has the lowest ionization energy, I should say first ionization energy, and helium has the largest first ionization energy, meaning it takes more energy to remove electrons from fluorine and helium and oxygen in that corner, and less energy in the opposite corner here. Why does that make any sense? Okay. Well, before we do the why, let's just practice on the periodic table again. Okay, 4 potential questions on the quiz will be, which element has a higher first ionization energy? So if you're asked to, what has a higher first ionization? Beryllium up here or barium down here? Well, ionization energy increases as we go up the periodic table, so beryllium is higher, barium's lower. Or if I asked again between carbon and fluorine, carbon's here, fluorine's here, we increase to the right with first ionization energy, so fluorine has a larger first ionization energy, carbon would be lower. We could also do a diagonal one this way and get it right, but if we did a diagonal one this way, we have to say we don't know again because the trend has some limitations. We'd have to look it up in a chart, okay? Now, why do big atoms, why is it easier? Why does it require less energy to remove an electron from a big atom? And the answer is this. It's all based on size, okay? Smaller atoms hold electrons close and with more force because they're physically closer together. Whereas large atoms, they can't keep track of the outer electrons, okay? If we're going to steal an electron from sodium, we wouldn't steal this electron right next to the nucleus. We would steal the one really far away. And if it's far away, it's not held on as tight because of its positive-negative traction. The distance is longer, and so it's easier to remove. So big atoms. I sometimes use some pretty dark metaphors for this. If you wanted to kidnap something, right, or maybe like if a wolf wanted to steal a sheep, you wouldn't try to kidnap, I don't know, if this was like a metaphor for a teacher at recess, and these are all the electrons, are the kids at recess. If you wanted to like kidnap a kid from elementary school recess, the one standing right next to the teacher would take a lot of energy. You would try to go after the one far away from the protective, watchful eye of the teacher. Okay, and so I don't know if that helps or if that kind of makes you feel uncomfortable talking about that. But electrons far away. If you have a huge atom like cesium with 6 energy levels, right? The electron is so far away from the nucleus, it doesn't require much energy to pull it away. Okay, all right. The next pattern I want you to learn is electronegativity. Electronegativity. Electronegativity, here's the definition. Electronegativity is the strength an atom has to pull shared electrons toward itself. So we might not have as good of a background as I wish you did on this, but in bonding, covalent bonding, usually we talk about this, atoms are sharing electrons, but they don't share equally. Some pull tighter than others, and electronegativity is the strength of this, right? The strength an atom has to pull shared electrons toward itself in a bottom, because they don't always share electrons equally. Maybe if you and a sibling had to share a Christmas present or a car, you don't probably share as equally as your parents would like. And a little trick for this one, noble gases never share electrons, so they are not assigned an electronegativity value. So the pattern is very similar to the last one we just did, that as you go up the periodic table, electronegativity increases. And as you go to the right on the periodic table, electronegativity increases. But notice this, the pattern stops at fluorine. And the reason we stop at fluorine is we want to stop before we hit the noble gases. So going back down to our periodic table, the value, I should say, of electronegativity increases as we go towards fluorine and stops at fluorine. The noble gases don't have electronegativity values. Okay. So that is, again, multiple choice cousins. What's more electronegative, nitrogen or phosphorus? You would pick nitrogen as higher up. What's more electronegative? Between elements moving left and right on the periodic table, between nitrogen and fluorine, you would pick fluorine because it's farther to the right. Diagonal, what's more electronegative? Arsenic, sulfur, or fluorine, you would pick fluorine. Careful, I might trick you by throwing a noble gas in there. Never pick a noble gas. If I asked you what's more electronegative, oxygen or chlorine, you would pick I don't really know, because one's farther up and one's farther to the right. We could look up the value in a chart, and we'll be very familiar with that chart, but we can't do that ahead of time from just the periodic table. Okay? We want to explain why again. Why? Well, the why is based on the very similar thing. Why does electronegativity have this pattern? It's again based on size. When atoms share electrons, if they're physically closer to one nucleus, they'll get pulled more. So let me see if I can draw a quick example on this piece of paper here. So if we had a red atom, and let's make a red atom a fluorine atom. Fluorine has 2 rings, okay, with 2 electrons, and the second ring has 7 electrons. 1, 2, 3, 4, 5, 6, 7. Now I'm going to switch markers to a red atom, and let me pick a bigger atom. Let me pick, let's pick, I'm tempted to do iodine. That's a really big atom. Let's go for it. We have iodine, and iodine has 5 rings. There'd be 1 ring, 2 rings, 3 rings, 4 rings, and there's a 5th ring on iodine, which I'm going to kind of overlap like that to show us. Now, I'm not going to show all 53 electrons of iodine, but there'd be all kinds of electrons on these rings. But the key is this. There'd be 1 electron here from iodine that overlaps. And this overlapping is what we'll draw in a week when we start talking about our bonding unit, that this is sharing electrons when we draw it like this, right? And fluorine and iodine are sharing a couple electrons. And they're not really like cooperating like you learned in elementary school. They're like fighting over the electrons. And are these electrons closer to fluorine's positive nucleus than they are to iodine's positive nucleus? The answer is yes. And because of the physical closeness, the electrons are pulled more towards fluorine and less towards iodine. they're not pulled 100% of the time, but they're just pulled a little bit more here. Maybe the electron would do a couple laps around fluorine and then do a lap around iodine, right? Do a couple more laps over here, then do a couple laps around iodine. But it physically spends more time here, and it leads to all kinds of interesting chemistry with polar bonds and polarity. Electronegativity is a huge component of this. Okay. Now, there's one more pattern that is missing from this PowerPoint called electron affinity, which is a lot like looking at ionization energy with a double negative. So we will, I'll have you read a couple pages in your book about electron affinity. We'll talk about it really quickly, but to be quite honest, it's not as valuable as these other patterns. Okay, so I hope you learned the pattern, number one, of which atoms are bigger and why. A second pattern, which atoms are higher first ionization energy and then why. And then the third one, which atoms have a bigger electronegativity value and why. Give you some homework problems that are easier from the book. You can check those out. And then the next day in class, we'll study the whys more in depth and really try to dissect the perfect wording you'll want to use if given this question on an AP exam. All right, cheers. Check Google Classroom out for all the other information.